6:30 in the morning.
Don't care. Maybe not a good one. Is he the one that she had her copy?
When's that one? Last week?
I mean, it's before
When I was
practice.
tired, I was like, I'm a 40 and I was like, 45. This big kid in town. Yeah, I guess that's got me. Tired him.
I'll probably do it tomorrow morning.
So I guess I think somebody else is going to take him.
Right. This is lecture 13.
The wall.
Right. So where? Right here. Okay, so at the end of last class, we ended up talking about systems of first order ordinary differential equations, and we said that the ones we can handle are those that are linear and homogeneous, and they have constant coefficients. So the very basic systems of first order differential equations. And we ended up ending at solve the following eigenvalue problem. To arrive at a general solution for the system of first order linear constant coefficient ODEs. So the system that we have to solve is one that looks like this. And we can slightly modify the system by introducing the identity matrix on the right hand side. And that's perfectly equivalent. Remember the identity matrix? It's just a matrix with ones in the diagonals and 0 elsewhere. Is the equivalent to the number 1 in linear algebra and matrices. So basically anything that multiplies an identity matrix, as long as the dimensions are compatible, remains anything. Identity matrix times x is equal to x. So collapsing these terms here, we'll find that a minus lambda I times x is equal to 0. Alright? So what are the options for these? Well, either this is a product of a matrix times a vector. So for these to be 0, either the vector has to be 0 or the matrix has to be 0. So how do we state this? For the expression above to be true, either x is equal to 0 or the determinant of a minus lambda I is equal to 0. Since the option leads to a trivial solution, remember that the solution of the system of ordinary differential equations was going to be of the form, let's write it again, we're going to try a solution such that y of t is equal to x e lambda t, and therefore that leads to y of t being equal to 0. Then the only admissible choice for a non-trivial solution is that the determinant of a minus lambda I be equal to 0. So solving that equation leads to the eigenvalues. So the solution of the equation, determinant of a minus lambda I is equal to 0 leads to the eigenvalues lambda, and there's multiple eigenvalues. You'll have as many eigenvalues as the size of the matrix, as many as the size n of the matrix A. Once eigenvalues are determined, the eigenvalues, the eigenvectors may be found by the original expression a minus lambda I times x is equal to 0. So we plug it back in there. Each eigenvalue will lead to one eigenvector x, and then leading to the solution of the system. Leading to the solution of the system, or the system of ODEs as, well, there's one possible solution which is equal to x1 e to the lambda 1t lambda 2t, and finally y of t n is equal to the nth eigenvector e to the nth eigenvalue to the power t. The general solution y of t is a linear combination of the ones above. So the general solution y of t will be equal to c1 times the first eigenvector times e to the first eigenvalue to the power t plus c2, linear combination of constants times functions of t. And each of these functions of t is just an exponential function plus Cn xn e to the lambda n t. Okay. So that's how it goes. We start with a system of simultaneous equations, which have to be first order, linear, homogeneous, constant coefficient, ordinary differential equations that are coupled together. And in order to get to the answer, we need to solve an eigenvalue problem, solve for the eigenvalues, solve for the eigenvectors, and then plug the solution and linearly combine them like that. With as many, we'll have as many eigenvectors and eigenvalues as the size n of the matrix, and therefore we'll have as many coefficients or constants of integration there, C1 through Cn, to determine as many coefficients or as many, or the size of the matrix n. Now those coefficients then we can fix with initial conditions. Every single one of the solution, or every single one of the state variables, y1, y2, y3, has to have an initial condition that will be used to find the particular solution by fixing all these values of c. All right, so let's work on an example. You'll see that this is actually pretty simple. So find the solution of the system of ODEs below. Okay, so we have dy1 of t dt is equal to minus 3 y1 of t plus y2 of t. dy2 of t is equal to y1 of t minus 3 y2 of t. So as you can see, n equals 2. So we have two coupled equations. Coupled again meaning that you cannot solve the first equation for y1, whatever y1 represents. It can be a pressure, it can be a flow rate, if this is a hydraulics problem. It can be the position of an element in a mechanism, if this is a kinematics problem. It can be a voltage or current, if this is an electric circuit problem. Well, you cannot solve for y1 if you don't know y2. If you cannot solve for y2 if you don't know y1. So these are simultaneous, and you cannot get away from it. Again, this can represent any problems of the ones we talked about, and obviously additional more. So this is linear. As you can see, there's none of the y's are multiplying each other. They're not squared, cube, or in square root. None of the derivatives are multiplying anybody. Linear. It is homogeneous. We don't see any independent terms. All the coefficients are multiplying either a derivative or the zero derivative, which is y1, y2 versus y's. Constant coefficient. First order system of OD. Constant coefficients because the coefficient multiplying the y's, as you can see, minus 3, 1, 1, and minus 3 are all constants. None of them are a function of time. With initial conditions, y1 at 0, let me see, is equal to 2, and y2 of 0 is equal to 0. So those are the initial conditions. Remember, we need at least one of the initial conditions needs to be non-homogeneous. Otherwise, the solution of this system is trivial. It's 0. Okay? Because the governing equation is homogeneous, an admissible solution is 0. If I pick y1 equals 0, that satisfies this equation. If I pick y2 is equal to 0, because the equation is homogeneous. Alright? So that's an admissible solution, but that's not the solution we want. So to end up with a particular solution that happens also to be, that would be non-trivial, at least one of the initial conditions needs to be non-homogeneous, like this one. So that's enough. Okay, so this means also that y0 is equal to 2 and 0. Alright, so if we express a system y dot of t is equal to a times y of t, that is a linear homogeneous constant coefficient first order systems of ODE, then what is a? In this case, it will be minus 3, 1, 1, minus 3. Well, in this case, it happens to be a diagonal matrix, but that doesn't always have to be the same. I'm sorry, a symmetric matrix. Again, but that doesn't have to be the same, the case. All right, so we're going to solve the eigenvalue problem. Solve eigenvalue problem. The determinant of a minus lambda I must be equal to 0. So the determinant of the matrix minus 3 minus lambda 1, 1 minus 3 minus lambda must be equal to 0. Right? That's just a minus lambda I. Lambda I being just right here. Lambda 0, 0 lambda. So a minus that is minus 3 minus lambda, 1, 1 minus 3 minus lambda. Okay? So the determinant, remember, is the multiplication of the diagonal minus the multiplication of the counter diagonal. This was a 3 by 3 matrix, then we have to go all the diagonals positive and all the counter diagonals negative. Minus 3 minus lambda times minus 3 minus lambda minus 1 times 1 is equal to 0. So that leads to 9 plus 6 lambda plus lambda squared minus 1 is equal to 0. And that would be lambda squared plus 6 lambda plus 8 is equal to 0. So we have to solve this equation for the eigenvalues. So in order to solve that quadratic equation, remember, lambda 1 and 2 will have two solutions to a quadratic equation. It will be minus b plus minus the square root of b squared minus 4ac over 2 times a. So that leads to lambda 1 being equal to minus 2 and lambda 2 being equal to minus 4. And these are the eigenvalues of that system. Alright, it's usually appropriate to order the eigenvalues from higher to lower, not in absolute value and in actual value. So minus 2 being the highest is eigenvalue number 1, and then from there on, the lower values. Let's write this usually sorted from max to min. There's a reason for that. There's some special characteristics about that matrix that are gathered by the sequence of eigenvalues, especially the ratio of the highest to the lowest eigenvalue has special meanings. All right, so now we need to determine eigenvectors. Eigenvectors. We need to determine x1, so an eigenvector that corresponds to the first eigenvalue, and eigenvector 2. An eigenvector that corresponds to eigenvalue minus 4. So we say A minus lambda I multiplied times x is equal to 0. So for lambda equals lambda 1, which is equal to minus 2, we get minus 3 minus minus 2, 1, 1, minus 3, minus minus 2, x1, x2 of eigenvector 1. So that would be 3 plus 2 is minus 1, 1, 1 minus 1 times x1, x2, eigenvector 1. So, following to this point? Okay? Alright. Now the same process will happen if your system of equations is 3 equations, 4 equations, as many equations. It's just that first the eigenvalues on a system of equations that has 3 equations will require the solution of a cubic equation. Okay? If you have 4 equations, you'll have to solve a order 4 equation for the 4 eigenvalues. And then plug them in one by one to determine the corresponding eigenvectors. So this is a system of equations, minus 1 times x1, 1 times x2. 1 times x1 minus 1 times x2. And they're both equal to 0. Okay? So this leads to a system of equation minus x1 plus x2, x1 minus x2, well, first one equal to 0, second equal to 0. So we have a system of 2 equations with 2 unknowns, x1 and x2. Notice anything wrong with these system of equations? Huh? Yeah, x1 equals x2. And this one, what does the other one say? x1 equals x2. These 2 equations are actually the same equation multiplied by minus 1. So these equations are not linearly independent from each other. There's infinite solutions to the system of equations. Okay? And that would always happen when you're solving an eigenvalue problem. So you need to fix one of them and then calculate the other. And if you had 3 equations, if the original system of ordinary differential equations was 3 equations, you're going to end up with 3 equations here where one is a combination of the other 2. So you need to fix one value to obtain the other 2. So you arbitrarily set one value. Let's say I'm going to pick x1 be equal to 1, and x2 is going to end up being equal to 1. Same here. See? By the way, these 2 equations are homogeneous. So an allowable solution will be 0. Right? But we don't want 0, 0. Okay, so this same equations that means infinite solutions. So pick one, so fix one, let's say x1 is equal to 1, then x2 will be equal to 1. And therefore, the eigenvalue, or the eigenvector 1, that corresponds to the eigenvalue lambda 1 is equal to 1, 1. And that's going to be irrelevant later, as you will see. Because remember, we'll construct the solution y as a linear combination of this eigenvector with the other eigenvector, and we'll multiply by constants. So whatever value we pick is going to be multiplied by a constant anyway, so it is irrelevant. So it's always appropriate to pick one. It's the easiest one. Just don't pick 0. Alright, so for the second eigenvalue, which was lambda equals to lambda 2, which is equal to -4, then the system of equations becomes -3 minus -4, 1, 1, -3, minus -4. And now we're solving for the second eigenvector. So we have -3 plus 4 is 1, 1, 1, -3 plus 4 is 1. So we have that matrix. And now it is even more clear that the two resulting equations will be the same. So the resulting equations, as you can see, is x1 plus x2 is equal to 0, while the other one is also x1 plus x2 is equal to 0. Again, same equations leading to infinite solutions, or an infinite number of solutions. So what we do is just fix one of them. Usually pick x1 equal 1. That would lead to x2 being what? -1. So the second eigenvector that corresponds to the second eigenvalue is this. Right? So now we have two eigenvalues, two eigenvectors. Combining for the general solution such that y of t, which is equal to y1 of t, y2 of t, is equal to c1 times x1 e to the lambda 1 t plus c2 x2 e to the lambda 2 t. So again, we have y of t that is composed of two solutions, y1, y2 is equal to c1 times the first eigenvector, which is 1, 1, times e to the -2t, plus c2 times the second eigenvector, which is 1 minus 1, e to the -4t. there's a general solution. So y1 will be c1 times e to the minus 2 plus c2 times e to the minus 4t. y2 will be c1 times e to the minus 2 minus c2 times e to the minus 4. Alright, now it's time to find the particular solution. Right? So to find the particular solution, we need to impose y of 0 is equal to 2 and 0. Right? So that means that y1 of 0 is equal to c1 times 1 times e to the minus 2 times 0 plus c2 times e to the minus 4 times 0, and that would be equal to 2. And y2 of 0, which is equal to c1 times 1 times e to the minus 2, 0, plus, minus c2 times minus 1 minus c2 e to the minus 4 times 0 is equal to 0. Is that clear? So now the two equations will be, well, e to the 0 is always 1. This will be c1 plus c2 is equal to 2, and c1 minus c2 is equal to 0. These are two truly independent equations. We can add them, subtract them, whatever we need to do to solve them. If we add them, we get 2c2 is equal to, right? So this leads to the solutions that c1 is equal to 1 and c2 is equal to 1. We subtract them, same story. So the particular solution looks like y1 t is equal to c1, which is 1 times e to the minus 2t, plus c2, which is 1 times e to the minus 4t, and y2 of t is equal e to the minus 2t minus e to the minus 4t. Well, these can be expressed again as y of t is equal to 1 e to the minus 2t plus 1 minus 1 e to the minus 4t. Same thing. Particular solution. This set of solutions satisfies both the governing equation, satisfying both y prime of t is equal to minus 3 y1 of t plus y2 of t, and y prime of 2, or y2 prime is equal to y1 of t minus 3 y2 of t. That's the original system of ODEs, and y0 is equal to 2, 0. You can try it. Take the derivative of first one here. First of all, check if these satisfies the initial condition. At time equals 0, you get 1 plus 1 is 2, and 1 minus 1 is 0. You get 2 and 0. Okay? If you take the derivative of the first one, you get minus 2 e to the t minus 4, minus 2 e to the minus 2t, and minus 4 e to the minus 4t, and that equates to 3 times the first one negative plus the second. And so is the case for the second equation. So this solution here satisfies both this and this, as we went through the process. Again, this process applies regardless of the size of the system. Obviously, what would make it difficult is if you have a system with more than 4 equations. How do you solve the eigenvalues if you have an equation of order 4? How do you solve a order 4 equation for gamma? You find the roots of that. It's not trivial. Actually, there's a mathematical demonstration that says that there cannot be an analytical technique to solve an equation, the roots of an equation of order 5 or more. Okay? There was a French mathematician in the 18th century called Galois, whose contribution to mathematics before he died at the age of 19 on a sword duel was he proved that nobody, and that has actually stood for 150 years or so, that nobody can come up with an analytical solution method of a 5th order equation or more. Okay, you can do it numerically, find the roots of that equation, but not analytically. All right. So that's it. Now, obviously, this method is not terribly complex, but also the equations that we were given were not terribly complex. It's first order, linear, constant coefficient, homogeneous equations. There are not many phenomena out there that are governed by this simple set of equations. So what will be confronted, even if we do a simple circuit, electric circuit, and put a couple of diodes, not diodes, but I'll make it nonlinear, put a couple of resistors and put a couple of compliances or capacitors and solenoids, we'll end up with a system of equations, a couple system of equations for the currents and the voltages on the circuit, and those are not going to be constant coefficient. Well, they might be, but they are definitely not going to be homogeneous, and definitely not a 2x2 system. So more than often, we'll be confronted with systems that are far more complicated than this. So what do? We cannot rely on an analytical method. We need to do it using a numerical approach. So this method only applies to linear, constant coefficient homogeneous systems of ODE. In general, we can express a linear variable coefficient non-homogeneous system of ODEs as, well, we already saw this form, y dot of t dot is equal to the state matrix, which now can be a function of t. If at least one of the coefficients is a function of t, then this no longer is a constant coefficient equation or system of equations, plus the independent terms g of t, which makes the equation non-homogeneous. So if at least one of these is non-zero, even if it's just one, and even if it's just a constant, then the whole system is it's no longer homogeneous.
Can you
Wait.
repeat that last statement?
What's that?
Can you repeat the last statement? As far as the thing homogeneous.
So, give me a second. So the system of equations that I'm showing here is a system of equations that has variable coefficients because the matrix has at least one element of the matrix at least is a function of time. Okay? That will make it A or T, otherwise it would just be A. And it will be non-homogeneous because of these forcing term right here. This is an independent term. It's not multiplying any y's, it's not multiplying any y dots. Okay? So if at least one of these, or one of the entries on this vector is different than 0, even if it's just the number 1, even if it's just a constant, then the whole system ceases to be homogeneous. And therefore the method that we developed doesn't work.
Gotcha.
Okay? So, but that system is solvable. It has to be. It's linear. It just has variable coefficients, and it's just not homogeneous. So we are guaranteed a solution that is unique for the system, a unique set y of t. Okay, y1, y2, y3, but it's a unique set. Now, because we cannot do it analytically, there are, however, some analytical attempts, but they're so cumbersome that it ends up being more work and less accurate than doing this numerically. Its solution may be approximated by a simple extension of the numerical schemes that we describe for single first order ODEs. And what are those? Well, we listed the Euler's method. Remember that is order delta t accurate. So the error will decrease as fast as you decrease delta t. The modified Euler, which is order delta t squared. So the error will decrease as fast as you decrease delta t squared. Points. Order delta t squared. And finally, remember Runge-Kutta, which is order delta t to the fourth. So this actually converges to the solution much faster. So it is just a simple extension. Just notice that you're solving more than one equation. So, and it would address any system like that. In fact, it can address any system even if it's nonlinear. Because remember, when we posed these methods or these schemes, we wrote the equations in slightly different form that allowed for those differential equations to be nonlinear. We wrote them as dy dt equals to some function f of y and t. So that function f is allowed to be nonlinear and so on. So, recall, a single initial value problem consisting of dy dt is equal to some function of y and t, and y of 0 equals to some y0. We now have a system of initial value problems, or an initial value problem system, whichever way we want to see it, and we can express it y dot is equal to a vector of functions of y and t. This expression like this, or this form, allows for the equations to be nonlinear. So if the equations happen to be linear, if the system is linear, meaning that we can write it as y dot is equal to a to the t, or a of t, sorry, times y of t plus g of t. Then the function f of y and t takes on the form a of t, y of t plus g of t. So when we implement the numerical methods, Euler's and so on, we can do it by assuming that the right-hand side function of each of the equations is each row of these particular vectors. So implement the numerical schemes exactly the same way looping over the state variables. y1, y2, all the way to yn. Okay, so if we do in Runge-Kutta, we need to calculate k1, k2, k3, and k4 for the first equation, which will be the first row of these. Then we need k1, k2, k3, k4 for the second equation, which will be the second row of these. Okay. So, since we already have one solution at hand, granted it's a homogeneous constant coefficient problem, so we have this solution corresponding to this equation and this initial conditions. Let's try it numerically and see how close we get to this one, right? And let's see if, in fact, the error actually decreases faster in Runge-Kutta schemes than compared to Euler's and so on. So let me know when you're ready. If you have any questions, and I'll move the scope to MathCAD. Ready? Okay. So, let me see. Okay. So here it is. So I've essentially done the same schemes. I just generated another MathCAD file, which I'll post on Canvas as well. And the only difference here, first I set up that implicit variable called origin, which is an internal variable of MathCAD, which will start every array at index 1 instead of index 0. I just made that difference here because I wanted to start at 1 instead of 0. It will be a little bit confusing if we say we have 3 equations and then k, which is the number of equations, equal to 2, because it will be 0, 1, and 2. That's the only reason why I went to origin equal 1. You can also set that through the menus over there, but since I got used to working with MathCAD long ago before menus existed, you have to set up all these internal variables like that by hand. Okay, so here's a system of equations. It's exactly the same as the one we solved analytically. This is a state system matrix. -3, 1, 1, -3. By the way, again, state system matrices do not need to be symmetric like this one. It just happens to be that this in this case it's like this. And I made it like that on purpose so that the eigenvalues were real. Okay? Well, real numbers. I didn't want imaginary or complex eigenvalues because then that will lead to trigonometric functions. So if one of the eigenvalues was, for example, a complex number, or just simply I, an imaginary number, how much is 2 to the it? That would be the sign of t. Okay, remember the Euler's identity? E to the minus I t would be cosine of t minus I sine of t. So it's a combination of sines and cosines. So just to avoid that, I'm just, if I give you anything on the homework or anything on the assignment or on the exams, it is going to be one that leads to real eigenvalues. Okay, so this is the exact solution. And I'm going to be comparing everything I get numerically to this. And again, I just arbitrarily say that I want to solve things until a final target time of 1 second. That's not necessarily seconds, it's just a dimensionless value of time. Whatever the physics behind these problems are, then that time will have some units. And I'm going to break this up into 10 time steps, and the size of each time step, therefore, it will be, this is an assignment, delta t is df over n, which happens to be 0.1. Then I'm going to be modifying this to see if it improves the solution, okay? Keeping the final target time at 1. So I am going to assign a range variable n, that's going to go from 1 to n plus 1, so we're going to have 11 entries from the initial to the last one. And the value of time for each of these, for each of the values of the range variable n is going to be n minus 1 times delta t. So the value of time is going to be 0, 0.1, 0.2, 0.3, all the way to 1. Is that clear? Just stepping over the time values and the time steps. And k, lowercase k, is a counter for the number of equations. K, big K is equal to 2 is indicating that we have 2 equations. This is a system of 2 coupled ordinary differential equations. Okay? So I'm creating an array called yx, x for exact, that has a range n associated with it, and it has a range lowercase k associated with it. So it's going to have as many entries on the first row as you have time steps, and as many entries on each of the columns as you have equations. So if I print yx, I'm going to say here, give me yx. Remember, I have to be below or to the right of the definition. So I say equal. This is what I'm going to get. I'm going to get 2 columns and 11 rows. Okay. So column number 1 is y1, it's this solution, and column number 2 is y2, is the second solution, for all 11 values of time that I define, from time equals 0 to time equal 1. Alright, so let me delete this, and if I were to make, let's say, n equal 20, well, this array then is going to have 21 entries. That's simple as that. Okay, so 10, let's just keep it at 10 for now. So here's the Euler's method. The only difference now, this is exact implementation of the Euler's method as we had last class, with a single K1, a single predictor. There's no predictor and corrector, it's just a predictor and that's it. Is that I am looping within the loop. Okay? I am looping that for every y, every state variable, so I'm going y1 and y2, I am calculating the corresponding values of k1, right? So, and since the function f is not defined, what I have is a and g, this is a, and this is g, right, corresponding to that equation. All right, so I'm going to post that, you can analyze it, change things, debug it. It has no bugs, but you can introduce some and play with them. The modified Euler consists on 2 coefficients k, k1, k2 is a predictor and a corrector. And then you just step, half a time step to the right, and then step a full time step to the right. There it is. The Hoynes method is also a second order method, and it consists of stepping 2/3 of the way to the right, and then the linear combination of the coefficients will give you the prediction of at the next time level. And the Runge-Kutta requires 4 of these. Okay, K1, K2. So the only difference is that I am looping within the loop. I'm creating a nested loop there for the number of state variables from K equal 1 to capital K. In this case, capital K is equal to 2. Okay, not to be confused. Again, this maybe this was a poor choice for nomenclature. This K has nothing to do with K1, K2, K3, and K4. These are the coefficients of Runge-Kutta, of the Runge-Kutta scheme, and capital K is just the number of equations that we have. Okay, so the coefficients are all the same, everything's exactly the same, and this is what we get. This is the qualitative comparison of the solution. So I'm comparing the exact solution, that's the red, to Euler's, dark blue, light blue is modified Euler, magenta is Hoynes, and purple, I think, is Runge-Kutta. And as you can see, I'm comparing between time equals 0 to time equal 1. Obviously, Euler's is the one that does the poorest job, it lags behind the solution. And I am comparing state variable 1. See, I'm comparing, we have two state variables, y1 and y2. I'm comparing state variable 1. And if I make this k equal 2, then I'll be comparing solution 2. Solution 2 being, again, e to the minus 2t minus e to the minus 4t. Solution 1 is e to the minus 2t plus e to the minus 4t, and the other one is minus. So there's the Euler's doing a poor job. If I look at the residuals, let's make this 1 and compare the residuals of solution 1 and the residual of Euler, modified Euler, Hoynes, and Runge-Kutta. Let me make sure that this is updated. Yeah, 4%. 0.5% and 0.0003%, and if I make, let's say, this equal to 100, I'm going to increase it or decrease delta t by tenfold. The solutions now appear to be staggered on top of each other, and these values. So this, the Euler, since it's order delta t accurate, this should go to about 0.4, right? If I update it, 0.39. This one should go to 100th of what it is right now because it's order delta t squared. But if I update, it's actually even better than 100. At 9, remember we're talking about orders of magnitude, not exactly. And this one, then it should not even be appreciable, 10 to the minus 7, because Runge-Kutta will be 10,000 times better than before because we increase or decrease the time step size to 10-fold. Okay. What is the case for solution 2? I'm going to go back to and make the number of time steps 10. Solution 2 looks like that. Obviously, the Euler's method is not doing a great job. Let me update this. That's looks like more than 1.6%. Oh, all right. There's an error here on the denominator. Notice that I am trying to scale the residual to the maximum and minimum value of the exact solution, but I'm not specifying of what column of the exact solution. Right? I should say the column 6, control 6, the kth column of the exact solution. Kth column of the exact solution. See if that works. Yes, and it's indeed 13%. It's much more than expected. So let me fix this equation. The kth column of the exact solution. Control 6 acts as a specific column in a 2D array. Control 6K. Control 6K. Control 6K. Control 6K. Okay. So here it is. I got 13%, 2.8, 2.8, and 0.028. And those are the errors on those approximations. Obviously, the Runge-Kutta does the best job. If I decrease this value, the value delta t tenfold, I should get 10 times improvement on the Euler solution, this should be 1.3 when I update it. There it is, 1.03, a little bit better. This should be 100 times better, so it should be 10 to the minus 2 or so. There it is. And this should also be the case, and this one will actually be 10 to the minus 7 or whatever, 10 to the minus 6. Okay, so it is consistent with the theoretical definition of the method. Remember, we derived those from Taylor series, and by truncating the Taylor series at a particular term, we can very easily determine what is the level of accuracy and the speed of convergency of these methods.
So, would it just in general then be best just to use like the Runge cutter, or is it depending on the problem you get, depends on which?
Yeah, it depends on the problem.
Okay.
It depends on the problem, and it has a lot to do with the physics of the problem. Runge-Kutta is an even order method, order delta t to the fourth. That means that it will introduce artificial damping. So if you have a solution where you're actually expecting a high degree of oscillation, sometimes it's best to use an odd order method because it will not introduce damping, artificial damping. This is what we found last class, remember?
Yeah.
When we found last class, we went to, so using a higher order method is not necessarily, or generally, the right way to go. But last class, we did lecture 12. We were doing this one, which is a single ODE. And if you evaluated this at time equal 10 seconds, this is a solution that we'd expect, right? Well, it's obviously a wrong solution. We have too few time steps, so let's make this 100 time steps. See? The exact solution is the red one. And look at the Runge-Kutta, it's all over the place. It's actually diverging here because you're expecting this high degree of oscillation. So the red solution, actually the best solution in this case is Y2. And Y1, which is the first order Euler, is doing actually a decent job. If you make this 200, we'll see a slightly better solution, but because we have a high degree of oscillation, notice that the Runge-Kutta solution, which is the black one, still not catching up. You're quite right. Okay? If you have a diffusive problem, if you have a problem where you expect everything to equilibrate, yes, the Runge-Kutta is the answer. Always. But there's a lot to do, it has a lot to do with the physics of the problem, the choice of method. All right, so that's it. Do you have any questions? So I'll post this on Canvas, and I'm going to post the solution, the homework solution, or the homework, not solution, the homework assignment. And remember, that's due 2 weeks, 2.5 weeks from now. So you have time now to start looking at it. Obviously, there will be things there that you don't know how to address because we're still halfway through the material, okay? So have a nice weekend. I'll see you Tuesday. Today's Thursday, right?
Yeah. And we've only got class on Tuesday next week.
That's right.
Break.
Yeah, we have full break.
I'm not sure why they did that this year.
Yeah, they used to do Friday, Monday, right?
Yep. Oh, actually that does kind of make sense. So the Monday, Wednesday, Friday class is going to get twice.
Yeah. Especially this semester where they started doing